Welcome, Dr. Kitchen, to our discussion. Your recent article, Beyond the Fourth Paradigm of Modeling in Chemical Engineering, published in Nature Chemical Engineering, has generated significant interest. Could you give our listeners a brief overview of your key findings?
Certainly, Sarah. My colleagues, Victor Alves and Carl Laird, and I explore how modeling in chemical engineering has evolved through four main stages, each stage built upon the previous one, with each advancement driven by technological progress. We argue that we're now at a point where differentiable programming and machine learning are revolutionizing the field, moving us beyond the established fourth paradigm.
Can you elaborate on these four paradigms? I imagine our audience would appreciate a clearer understanding.
Of course. The first paradigm relied on simple correlations, like those found in steam tables. No need for deep physics understanding, just knowing how to use the tables correctly. The second involved manual fitting of mathematical models to experimental data, often using graph paper and basic statistical tools. The third paradigm saw the rise of computers, enabling multivariate and nonlinear regressions, a huge leap forward in analytical power. And finally, the fourth paradigm involves using machine learning, sophisticated algorithms that are very data-driven, somewhat akin to the first paradigm in that the physical mechanisms are less critical.
So, machine learning doesn't need an understanding of the underlying physics to function? That seems counterintuitive.
It's a valid question. While some sophisticated models blend machine learning with physics, this fourth paradigm model type often can work quite well without such knowledge. It's more focused on statistical relationships within the data itself. The emphasis shifts from understanding the why to predicting the what.
That's fascinating. Where does differentiable programming fit into this picture?
Yes. Differentiable programming, powered by automatic differentiation, is the key technological innovation underlying the success of modern machine learning. Think of it as a way to quickly and efficiently calculate derivatives within software. Derivatives are crucial for many calculations in chemical engineering, and this makes a significant difference in the speed and feasibility of many modeling tasks.
And how does this impact chemical engineering research and practice?
The impact is profound. It enables more efficient optimization, better sensitivity analysis, more sophisticated uncertainty quantification methods, improved process control strategies, all by making derivative calculations far faster and easier. It opens the door to rapid prototyping and development of new models. We gave some examples in the article regarding rate control and complex reaction networks and inverse problem solving.
What are some of the challenges in fully implementing these advancements?
One significant challenge lies in educating the workforce. Differentiable programming and advanced machine learning techniques are relatively new. Many current chemical engineers haven't been trained in these areas. While younger engineers are getting more exposure to these new fields as they come online, there's a significant need to bridge that gap through new educational programs and upskilling initiatives for the broader workforce.
So, it's not just about adopting new technology, but also integrating it with established domain expertise.
Exactly. Successfully leveraging these new techniques requires the combination of deep chemical engineering expertise with advanced data science and machine learning skills. It's about a thoughtful integration, not simply a replacement of old methods with new ones.
Dr. Kitchen, thank you for this enlightening discussion. To summarize, you've highlighted the evolution of modeling in chemical engineering through four paradigms: the central role of differentiable programming and automatic differentiation in accelerating progress in machine learning, the need for integrating domain knowledge with these new techniques, and the challenges and opportunities in upskilling the current workforce and educating future generations of chemical engineers. Your research provides valuable insights into the future of this field.
My pleasure, Sarah. Thank you for having me.